Hey everyone, and welcome to The Explainer. Today we've got a truly fascinating topic lined up for you. Our goal is simple, but honestly pretty ambitious. We're going to unlock the foundational architecture behind almost every single modern deep reinforcement learning method out there right now. If you've ever wondered how advanced AI agents actually learn to balance exploration, evaluation, and action without completely falling apart, well, you're in the right place. We are going to demystify the absolute DNA of modern AI by breaking down the Actor-Critic model. Okay, let's dive into this. Here's our roadmap to break this complex journey down into 6 logical steps. First, the variance problem. Then, enter the Actor-Critic, calculating the advantage, A2C versus A3C, avoiding common pitfalls, and finally, the foundation of modern RL. All right, starting off with part 1, the variance problem. To really appreciate the elegance of modern systems, we have to look back at the brutal frustration and, honestly, the mathematical noise of early reinforcement learning. Early on, engineers relied on Monte Carlo returns to figure out if an action was good or bad. But here's the kicker. Those returns can easily swing by over a factor of 10 between different episodes. Just think about that for a second. When your feedback loop has a 10x variance, it creates a massive, massive problem for any AI trying to find a stable path forward. It's just pure chaotic noise. And this brings us to a classic algorithm you might know, vanilla reinforce. Now, vanilla reinforce fundamentally works, sure, but the variance, it's terrible. Because it relies entirely on those raw, noisy returns we just talked about, training an agent with vanilla reinforce is quite literally like trying to learn how to play darts while riding a roller coaster. You're multiplying all that noise by your policy gradient and averaging it out, which produces a gradient estimator that takes thousands upon thousands of episodes just to move the policy a tiny, effective distance. It's painfully inefficient. So the big question is, how do we fix this? That takes us to part 2, enter the Actor-Critic. This is the elegant solution to our massive variance problem. We introduce a system with dual protagonists, effectively separating the act of making a decision from the act of evaluating that decision. First up on stage, we have the actor. The actor is your policy network. You can think of it as the charismatic performer out there in the environment, actively making decisions, taking actions, and being updated using policy gradients. But because it's out there trying all these new things, its performance can be pretty chaotic. It desperately needs some guidance. And that is exactly where our second protagonist steps in, the critic. The critic is the value network. Instead of taking actions, it simply observes the state and estimates the expected return. Visualize the critic as a steady, wise, low-variance teacher sitting right in the front row, carefully watching the actor's chaotic performance and giving stable, grounded feedback based entirely on what it expects to happen. So the crucial point is how these two interact to create what we call the advantage. We calculate this by taking the raw return, which we'll call G, and subtracting the critic's baseline estimation. What you're left with is the pure advantage. It tells the system something incredibly useful. An action is good if it produced an above-average return, and it's bad if it produced below what the critic expected. The critic gives the actor this nice, low-variance baseline, stripping away all the noise of that roller coaster and leaving only the actual quality of the action. Moving right along to part 3, calculating the advantage. Now that we know what the advantage is conceptually, we need to peek at the math behind it, because getting this right means balancing 2 competing statistical forces. When you calculate the advantage, you generally have 2 standard forms to pick from. On one side, you've got the Monte Carlo, or MC advantage. This is unbiased, which is awesome, but it has much higher variance because it relies on the full sequence of rewards. On the other side, we have the temporal difference, or TD advantage, sometimes called the TD residual. Now, this one is biased because it relies heavily on the critic's own estimations to bootstrap, but the payoff? It has far lower variance. It's much, much smoother. But what if you didn't have to strictly choose one or the other? Enter Generalized Advantage Estimation, or GAE. I want you to imagine GAE as a physical dial on your control board, labeled lambda. If you turn lambda all the way down to 0, you get pure TD, so low variance, high bias. If you crank it all the way up to a 1, you get pure Monte Carlo, unbiased but incredibly noisy. By 2026, the industry default is to set this dial to exactly 0.95. That specific setting magically hits the perfect bias variance sweet spot for most complex environments. Which brings us to part 4, A2C versus A3C. Okay, we understand the math now, but we face an engineering fork in the road. How does this beautiful math actually get executed on physical computer hardware? And this brilliantly illustrates the evolution of deep reinforcement learning hardware over the last decade. Back in 2016, a method called A3C was king. That stood for Asynchronous Advantage Actor-Critic. It spawned multiple worker threads across CPUs computing gradients locally and asynchronously pushing them to a server. But fast forward to the 2026 landscape, and A2C, the synchronous version, absolutely dominates. Why is that? Well, because A2C runs multiple parallel environments synchronously in a single process, stacking all those observations into giant batches. And GPUs absolutely love large batches. A2C gives you massively higher GPU utilization, plus it's completely deterministic. Regardless of whether you're using CPUs or GPUs, training these two networks requires a combined loss equation. It has three vital parts acting in concert. First, the policy gradient loss to train the actor. Second, the value regression, which is really just the critic trying to match its predictions to the actual returns. And third, and this is highly critical, the entropy bonus. This acts as a mathematical incentive to keep the actor actively exploring different actions, rather than just getting lazy and repeating the exact same safe move over and over again. Next up, Part 5, Avoiding Common Pitfalls. Now, as elegant as this all sounds in theory, building it can be an absolute nightmare if we aren't careful. Structurally, building this architecture from the ground up follows a clear four-step process. Step 1, you initialize the critic to create your baseline. Step 2, you calculate your end-step advantage to find out how good your actions really were. Step 3, you perform that combined loss update we just went over on both networks. And Step 4, you parallelize the environments to gather enough diverse data. Sounds easy enough, right? Well, here are the brutal pitfalls that will silently ruin your training if you're not paying attention. First, critic bias before the actor gradient. Look, if your critic is completely random at the start, its baseline is pure noise. If you don't warm up that critic for a few hundred steps before turning on the actor's gradient, you'll feed pure garbage straight to your actor. Next, forgetting advantage normalization. You absolutely must normalize your advantages to stabilize training. Then, ignoring the on-policy contract. A2C data can only be used for exactly one update, period. Furthermore, if you set your entropy bonus too low, you'll suffer from entropy collapse, where your policy just stops exploring completely. And finally, unscaled rewards will just completely mess up your gradient magnitudes. Seriously, keep your eyes peeled for these traps. And finally, Part 6, the foundation of modern RL. If we can successfully navigate those pitfalls, we basically unlock the keys to the kingdom. Let's move to and see how this builds out across the AI landscape. When we look at the most famous AI models today, we're really just looking at A2C with some specific upgrades attached. PPO, which powers so many large language models, it's just A2C with a clipped importance ratio. Impala is basically A3C with an off-policy correction. SAC is an off-policy A2C with a soft value critic. DPO? That collapses A2C into preference ranking. And the legendary Alpha Star that conquered StarCraft? That is literally just A2C with league training and imitation pre-training attached to it. It's all connected. And this brings us to a fantastic quote from our source material that I really want you to remember long after this explainer is over. If you see advantage in a 2026 paper, think Actor-Critic. The Actor-Critic model is the undisputed mental model for virtually every modern deep reinforcement learning method out there. It is the core DNA of the field. So here is a challenge for all of us as we wrap up. When you go to code your own environment, whether it's a super simple grid world or a highly complex robotic simulation, where is your bias and variance sweet spot? Try sweeping those lambda values, play with the GAE dial, and find that perfect, beautiful balance between the critic's bias guidance and the raw reality of Monte Carlo returns. Thanks so much for joining me on this deep dive today, and keep exploring.